All right, for the first one, HNO3. What's the name of that acid? Nitric acid. Nobody wants to talk. Nitric acid, and I have a concentration of 0.1 molar concentration of nitric acid, and I need to calculate the pH of that. What you need to know first off is nitric acid strong or is it weak? It's a strong acid, okay? Which means, since it's a strong acid, that it is going to have 100% dissociation. Really, it's like 99.99 something percent. But mostly, it's going to fully dissociate, which just means if you have HNO3, it's going to completely dissociate into hydrogen ions and nitrate ions. And this is all, everything dealing with acids and bases, they're all in solution, so these are all aqueous things. If my concentration is 0.10 molar, now with strong acids, it's super easy. You don't have to set up an ice table every time, but just so you can kind of see what's going on. If my initial concentration of nitric acid is 0.1 and my initial concentration of those guys is 0, when you fill in your change, you have minus x plus x plus x. The ice tables, when you're dealing with acids and bases, is sometimes a lot easier because you don't have a lot of coefficients to work with. There's just plus and minus x. So I have x here, and then 0.1 minus x. But what's going to happen is, since this fully dissociates, I'm going to end up with all of this breaking apart and turning into 0.10 molar of NO3 and 0.10 molar of hydrogen ions. Okay, full dissociation. So that means that this number down here is going to match that number up there. So if I have a concentration of 0.1 molar of nitric acid, and it's a strong acid, any strong acid, it fully dissociates. That means that the concentration of hydrogen after dissociation is 0.10 molar. So then you can just take the negative log of that to get your pH value. What's the negative log of 0.1? Do you know? It's just 1. So the pH is equal to 1. Does that make sense? Since it is a strong acid? Yes. By the way, the fact that it's a strong acid only means that it fully dissociates. It doesn't mean necessarily that it's going to have a super low pH. It just means that every molecule is going to break apart. But it should be an acidic pH. All right, next example. Find the pH of, kind of wrote over that, 1 times 10 to the negative 10 molar concentration of HClO4. HClO4 is what? Acid. What's the name? Perchloric acid. Okay? Is that strong or is that weak? Strong. It is strong. Okay, so that's good. It's actually, when you see a strong acid in one of these problems, it's like a happy thing because then you have full dissociation and it's easier to figure out the concentration of hydrogen ions. If my concentration of perchloric acid is 1 times 10 to the negative 10, and it's a strong acid, then that means the concentration of hydrogen ions is also 1 times 10 to the negative 10 after it dissociates. So then that seems really easy. Seems like you should just go ahead and plug in pH equals the negative log of 1 times 10 to the negative 10. But if you do plug that in, or if you know about logs, what is the pH that you get? You get 10. Does that make sense? No. It does not make sense. Perchloric acid I know is a strong acid. And so a pH of 10 is not the correct answer. So what you need to pay attention to is the concentration. This concentration is super small. You barely have any perchloric acid actually in there. Most of the solution is just water. And so if the hydrogen ion concentration is less than 1.0 times 10 to the negative 7, which 1 times 10 to the negative 7 is the hydrogen ion concentration in water. If the concentration of your acid, whether it's strong or weak or anything, is less than 1 times 10 to the negative 7, then it's so small that it doesn't affect the pH at all. So the pH just equals 7, which is a neutral pH. And so even though there is a little bit of that perchloric acid in there, it is not enough to even make a difference on the pH. It's basically like you just have water. Yeah?
No, it was just like a thought.
Okay.
Like, why would it not be 4?
Why would it not be 4?
Yeah.
What do you mean? Why?
You're not talking fluid. Well, yeah, I know, but it's an absolute split.
Why wouldn't it be like the difference between like 14 and 10?
Yeah.
Just because it's only because that concentration, this is not a valid calculation. Like what I calculated, it is not okay to do that. I was just showing like this is what you would get and this is why it's not going to work. But this number doesn't actually mean anything because it can't be done that way. So since the concentration is so small, it doesn't affect the pH at all. It's basically the pH of water, which is 7. Okay. All right, next one is what's going to happen now if I take 2 solutions and I mix them together. Then what's the pH? There's going to be some adding involved, yes. But it's just not that easy. Nope, you cannot. All right, in this one I've got 54 milliliters, 0.00125 molar of nitric acid mixed with 25 milliliters, 0.025 hydrochloric acid. What's the pH? So first of all, some things that you need to notice when you're dealing with mixing solutions together is the strength of the acids that you're working with, and then the total volume of the whole solution. So first of all, these are both strong acids, which means that you're going to have 100% dissociation of both into hydrogen ions and then nitrate and chloride ions. You first have to find, wait, I should have said, you must find first the concentrations after they're mixed together. So you have those solutions separate and then they get poured together in one beaker. And so you've got to figure out, well, what's the concentration then of the nitric acid after the solutions are mixed? What's the concentration of the hydrochloric acid after they're mixed? How do you figure out? We've done this before. Like I said, a lot of the stuff in this unit is not new. We're just like putting it all together in different new ways. How do you figure out final concentrations of solutions if you know their initial M1 and V1? M1, V1 equals M2, V2. So we are going to use that equation here to figure out what is the molar concentration of each acid after it's mixed together. Also, I know the total volume is the 54 milliliters plus 25 milliliters. That equals 79 milliliters of the total solution after they're mixed together. So now I'm going to look at each one separately. I'm going to start first with nitric acid. And I'm going to do the whole M1V1 equals M2V2 for that. My initial molarity of nitric acid is 0.00125. The volume of that is 54 milliliters equals M2 times the final volume, 79 milliliters. Solve for M2. M2 is 8.54 times 10 to the negative 4. Now what I really calculated here was just what's the concentration of the nitric acid after the two solutions are combined together. But since nitric acid is a strong acid and fully dissociates, if this is my concentration of nitric acid, it is also the same thing as the concentration of hydrogen ions that came from nitric acid. So now I need to go through and I need to do the same thing for HCl. And then you're going to add the two together. So M1V1, M2V2 for hydrochloric acid. My initial molarity for HCl is 0.025. That volume is 25 milliliters. M2, final volume, 79 milliliters. That molarity, M2, 7.91 times 10 to the negative 3. That's equal to the concentration of HCl, which when it fully dissociates is the same as the concentration of hydrogen ions that come from that. So now I'm going to take these numbers. So I have hydrogen ions that come from nitric acid. I have, these should all be molar concentrations. I have a concentration of hydrogen ions that comes from hydrochloric acid. I take those two numbers and I add them together to get your total hydrogen ion concentration. And it equals 8.76 times 10 to the negative 3 molar. And then from there, it's easy. The hard part is figuring out the hydrogen ion concentration. And then from there, all you have to do is take the negative log of that number because we know that equals the pH. The negative log of 8.76 times 10 to the negative 3. And it gets 2.06. Which makes sense. I combine two strong acids together, so my pH needs to be acidic. Questions on that process? Okay. That was the hardest one today, I think. You're not ready? You're not ready? That is correct. Okay, so you assume correctly. This one is super easy. The only difference is that, okay, I'm still, like I said, all the questions are asking you for pH. What is the pH? What is the pH? But you're dealing with different things. I've got sodium hydroxide. That's a base. Is it strong or is it weak? Sodium hydroxide? Strong. Okay, which means that, again, you have full dissociation, which when you're dealing with strong acids or strong bases, you do forward arrow only because it completely dissociates into ions, sodium ions in this case, and hydroxide ions. And so if I have 0.25 molar sodium hydroxide, then I'm going to have 0.25 molar concentration of hydroxide ions after the dissociation. Now when I negative log that number, 0.25, does that give me pH? It gives me POH. Okay, I can do that. It gives me 0.6. And I know that pH plus POH equals what number?
14.
14. So now I can go ahead and subtract. 14 minus 0.6 equals 13.4. That is your pH. Okay, and that's a basic pH, so that makes sense. Okay, you're going to be excited because you get to use ice tables on this question. Yes, because we are dealing now with weak acids. On page 637, it gives you like a list of steps that you can follow to, you know, what you need to do to go through and calculate the pH of a weak acid. But if I just go through this example, it will make sense to you. Again, the question is, what is the pH? I have 250 milliliters of 0.25 molar solution of acetic acid. Acetic acid is a weak acid, which means that it does not completely dissociate. Actually, very small percentage of the acetic acid molecules will actually break apart into hydrogen and acetate ions. So you need to start, and they give me a Ka value. Ka is the equilibrium constant based on the concentrations of the dissociated acid. So here's my formula for acetic acid. When you're dealing with weak acids, it requires a double arrow because the system is going to reach equilibrium in which some of the molecules will break apart and then they'll, like, you know, reform acetic acid, then other ones will break apart. So you're going to have like this circular equilibrium thing going on here. On the other side, I've got hydrogen ions. I've got acetate ions. Everything here is aqueous that we're dealing with in these solutions. When dealing with weak acids, you need an ice table. It gives me the initial concentration, 0.250 of acetic acid. Now, before any of it dissociates at all, I've got 0 here, 0 here. My change, minus x plus x plus x. At equilibrium, I'll have x of acetate ions, x hydrogen ions, and 0.250 minus x of acetic acid. And again, since the question is asking me for pH, my whole goal is to figure out the concentration of hydrogen ions so that I can just negative log it and figure out what the pH value is. Now, my concentration of hydrogen ions is x, so I need to solve for x, which you guys did in chapter 13. So it's kind of a review. First of all, and they give us the Ka value, so we have to remember that when you're writing equilibrium expressions, products over reactants of everything when we're dealing with aqueous, or with acids or bases, everything aqueous solutions. So on the top, hydrogen ions concentration, acetate ion concentration divided by the concentration of the leftover acetic acid they give me Ka, so Ka is 1.8 times 10 to the negative 5. I set that equal to, and then I plug in my whole equilibrium row into my concentrations here. So over x times x. And then I got these from my ice table. Over 0.250 minus x. K is super small, so that means x is super small. So I can cross out that x. Okay, so you end up with 1.8 times 10 to the negative 5 equals x squared over 0.25. X equals 2.1 times 10 to the negative third. That, if I look back up at my ice table, equals the concentration of hydrogen ions. So I can just negative log that number, get your pH. pH is 2.67. And then, don't write this. Hang on. An addition to that question would be once you go through and you figure out, you know, it's a weak acid, so you know that it doesn't dissociate 100%. You know that only some of it does. So an added question to that after you figure out concentrations and pHs and all that stuff would be, well, what was the percent dissociation of the weak acid? And so all you have to do is take your concentration of hydrogen ions, which was 2.1 times 10 to the negative 3 molar, and you need to divide that by what the concentration would be if it was 100% dissociation. If it was 100% dissociation, then the concentration of hydrogen would be 0.25, because that's what was given. So you divide that by your initial concentration of the acid, 0.25 molar. That gives you decimal. You times it by 100. Okay? So it's basically how much hydrogen did you get out of how much you started with. Times it by 100. That gives you a percentage. 0.84%. It should be a small number because it's a weak acid, so you're going to have a very small percentage of the molecules dissociate, break apart, and ionize.